Hello, bachcho. Today, we're going to tackle a very important topic from electromagnetic induction, Lenz's law. And I promise you, by the end of this session, this concept will be so crystal clear, you'll never forget it. And you will be absolutely ready for your exams.
Okay, let's get right into it. To get our brains warmed up, let's start with a really simple question. So we know from Faraday's brilliant work that a changing magnetic flux creates a current. That's fantastic. But you see, physics is a very precise science. It's not enough to just say, oh, a current is flowing. We have to know everything about it, including its direction. And that's the big puzzle that Lenz's law comes in and solves for us. To really understand this, let's not start with some complicated textbook definition. No, let's start with a simple character.
I want you to imagine you have a very stubborn, a very ziddy friend. You know the type, right? If you say, let's go left, they will definitely go right. If you want to study, they'll want to go play cricket. They just always do the opposite of what you want. Well, Lenz's law is exactly like that ziddy friend.
This slide, it simplifies everything down to one single idea: opposition. If you try to increase the magnetic flux passing through a coil, the new current that's created will generate its own magnetic field to fight that increase. And if you try to decrease the flux, guess what? The current will create a field to fight that decrease. It doesn't matter what you do. The induced current's one and only job is to fight the change that you are trying to make.
Okay, so now that we have this simple idea, this ziddy friend idea in our heads, let's look at the official definition. This is the one you need to write word for word in your exams to get full marks.
So this is the exact statement from your NCERT textbook. It sounds a bit formal, I know, but it's saying the exact same thing as our ziddy friend story. And you see Faraday's formula there? That little minus sign right at the beginning? That's it. That is Lenz's law in mathematical form. It's literally the symbol for opposition.
So, the most important point to get is this: the induced current is a reaction. It doesn't just pop up out of nowhere. It's a response. And its entire purpose is to try and cancel out the very change that created it. It just wants things to stay the same.
All right, we have the analogy, we have the official definition. Now, let's see Lenz's law in action with the classic magnet and coil experiment. This is where the theory becomes crystal clear.
Okay, look here. We've got a coil of wire, and we are pushing the north pole of a magnet towards it. Now, as the magnet gets closer and closer, more magnetic field lines are passing through the area of the coil. Simple stuff. So we can say the magnetic flux is increasing. So, what is our ziddy coil going to do? Well, it hates this increase in flux. It wants to stop it. So it's going to try and push the magnet away. It's going to try to repel it. And how do you repel a north pole? Simple. You create another north pole. So the face of the coil that's near the magnet will become a north pole.
And this brings us to the final step. To make that face a north pole, which way should the current flow? Well, we just use our right-hand rule. If you curl your fingers in the direction of the current, your thumb points to the north pole. So for the thumb to point outwards, away from the magnet, the current absolutely must flow in the counterclockwise direction. Simple enough. Okay, let's look at case 2. Now what happens if we take that same magnet and pull it away from the coil? Well, the number of magnetic field lines passing through the coil is getting less and less, so the magnetic flux is now decreasing. Oh, but the stubborn coil hates this change also. It doesn't want the flux to decrease either. To oppose this decrease, it's going to try and pull the magnet back. It will try to attract it. And how do you attract a north pole that's running away? You create a south pole.
So to create that south pole, we again use our right-hand rule. This time, the current has to flow in the clockwise direction. See? It doesn't matter if flux increases or decreases. In both cases, the induced current flows in a direction that opposes the change. It's perfectly consistent. But why? Why is nature so ziddy? Why this constant opposition? Well, the reason isn't just some random rule. It's actually connected to one of the most fundamental, most important principles in all of physics.
Now, pay close attention here, bachcho. This is super important. Many students, they just memorize the rule, but they don't get the reason behind it. And this is what I call a silent killer in exams. On those tricky conceptual questions, this is where you can lose marks if you don't know the why.
Let's just imagine for 1 second that Lenz's law was the opposite. What if the coil helped the change? So when you push a north pole towards the coil, what if it created a south pole? Well, it would attract the magnet. So you'd give the magnet a tiny little push, and the coil would pull it in faster and faster, creating more current, which creates a stronger attraction, making it go even faster.
You'd be getting energy for free. This would be a perpetual motion machine, and that violates the law of conservation of energy. Physics, you see, just doesn't allow for a free lunch.
So the whole point is, Lenz's law has to exist because you cannot create electrical energy from thin air. In the real world, the coil repels the magnet. You have to do mechanical work. You have to use your energy to push against that repulsion. And the work you do, the energy you spend, is what gets converted into the electrical energy in the coil. Energy is just being transformed from one form to another. That's all.
Chalo, let's quickly summarize all the key points that you need to remember for your exams.
Okay, so let's summarize. These points are the heart of the topic. First, Lenz's law gives us the direction of the current. Second, it always opposes the change in flux. That means an increase in flux leads to repulsion and a decrease leads to attraction. And finally, the most important one, this law is a direct result of the law of conservation of energy. I'd say take a quick screenshot of this slide. It's everything you need for a last-minute revision.
So I'll leave you with that final thought. When you stop seeing Lenz's law as just another physics rule to memorize, and you start seeing it as nature's way of balancing its energy checkbook, the whole concept becomes much deeper and actually much easier to remember. Keep studying smart.